Okay. All right, so as you know, the next lab coming up is going to be involving XBee wireless modules. So for the beginning of this class, we're going to cover an introduction to 802.15.4 IEEE standard and the ZigBee routing protocol. And then we're going to relate it back to the XBee modules and give relevance there. So what is the XBee? Super popular wireless development platform, so sure most everybody here has probably heard of it at least. It's a series of form factor compatible radio modules, and they're generally interfaced with UART. Some of the newer ones have optional SPI pins, but for the most part they're all communicated through UART. They come in a variety of standards. A lot of people think, well, I don't know about a lot, but some people think like ZigBee is synonymous with XBee, or some people have tried to, I've had correct me saying XBee to ZigBee, but that they are in fact different things. XBee's name is derived from ZigBee, obviously, but ZigBee supports a bunch of different protocols, and we're going to cover those in a second. And they've gained a lot of popularity through hobbyists, mostly because they're really easy to get into. By default, they come in a transparency mode. So they act as a UART cable replacement. So when you hook them up with just default settings, you can just transmit characters over the UART, and they just show up on all the other modules that are within your network. So it's easy to just you know, if you're using Arduino, serial.begin, just pump characters out through it and then sort through it on the other end and handle it that way. So that's how it's really gained a lot of its popularity as a module. But you can do a lot more with it than just be a hobbyist. So the different modules that are available, the first one that came out was 802.15.4 based one, which is an implementation of the MAC and physical layer of the routing protocol, or the OSI layers. And they called that Series 1 originally, but now if you go to the website, it's just labeled as 802.15.4. This module is not capable of any kind of like network operations, so you can only do point-to-point communications with it. There is the XBee ZigBee modules, which are running the full ZigBee stack, and they used to be referred to as the Series 2 modules. XBee also has some lower frequency modules, so they have a 900 megahertz version. And there's also an 800 megahertz version for European countries. And they also have a module called DigiMesh, which is running their own proprietary routing protocol on a 2.4 gigahertz bandwidth. And then they've most recently released a Wi-Fi module. And we'll probably be using those later in some different labs. So the 802.15.4 and the ZigBee modules are really where the XBee modules became popular. The 802.15.4 is a MAC physical layer only, so like I said, only point-to-point communication. And ZigBee is a protocol that runs on top of 802.15.4, which is why when you see it referenced half the time, it's ZigBee / 802.15.4. The XBee module itself, they contain a small like Freescale microcontroller inside, and they've recently introduced programmable modules, but for the most part, you're not allowed to modify the firmware in any way, and they're just there dedicated to running the ZigBee stack. And of course, this is a network protocol. It allows multi-hop communication. So let's take a look at the IEEE 802.15.4 standard. So the main emphasis of 802.15.4 versus 802.11 is they're focusing on lower power consumption, lower cost, a more simple protocol, and also it can run they can do either 2.4 gigahertz range or around 800 megahertz. So it's you have a few more options there, especially for low power applications. Here's a little graphic that kind of shows you where the 802.15.4 fits in with like the OSI or any other networking model. See at the inside the data link layer, it just has access to the MAC and some parts of the link control. And then of course the physical layer there at the bottom with the two different options I just mentioned. So the 802.15.4 MAC layer, that's providing data management services to the upper layers. It also gives you frame control, which with reference to the XBee modules is going to give you access to acknowledgements, which you might have to use for the lab. It has two different modes of addressing, one being the 64-bit like MAC address like you have on like your desktop computers or with any 802.11 protocol, but it also has a 16-bit network address that's assigned by the coordinator. So the 64-bit address is a set hardware address, and then 16-bit addresses become available when you've had a coordinator assign them. But if you're using the XBee 802.15.4 modules, you can assign those yourself because they don't have a network coordinator. So you can write code yourself that can behave as one. This is where, and I want to make a note right now, last year we ran into some trouble. We had a lab where we're using the ZigBee XBee modules, and I had a coordinator set up, and the way I had introduced it was to use a 16-bit addressing, but we had some older modules and some newer modules that were separated in purchase by about like probably 2 years. And since then the firmware had changed a little bit. So the 16-bit addressing was not addressing at all, it was broadcasting to the whole network. And so we had to use 64-bit addressing too. So when you're working on your lab, for these labs we're just going to get 16-bit addresses from our modules and address them like that. However, you should be able to use 16-bit addressing when you have modules all from the same time period and the same firmware running. So don't get the impression from this lab that you can't use 16-bit addresses, because they're just as valid. Whenever you're setting up a network that's not predefined and you haven't added all the devices yourself with 64-bit addresses, using the network address makes sense. So also on the MAC layer you have a frame check sequence. Normally it's 16-bit, but with the XBee modules you'll see it's 8-bit, but it's just a checksum type thing to make sure data is delivered successfly and uncorrupted. A few other features of the MAC, these XBee modules will use a CSMA-CA technique to determine when to broadcast. So that's carrier sense multiple access with collision avoidance. So it will check the channel to see if any other modules are transmitting on that frequency, and if it's clear, it'll transmit, and if it's not, it'll just sit there and wait until it opens up. The MAC address also, I mentioned with that frame bit, you can confirm successful data transmission with a little acknowledgement that it can send back to a transmitting module. And it also contains 3 different security features, one being no security, which I guess is a feature, and access control list, and symmetric key security, which is, when you look in the XBee, they call it AES, which I already forgot the abbreviation to that, but it's in the documentation. But just one of the security features available. So the physical layer, as we discussed earlier, has 2 different frequency bands you can choose from. 2.4 gigahertz is what we're going to be using for these labs. And it's available worldwide, has a higher data transfer rate, but a little more power consumption. Then you can choose between the 868 or 915 megahertz frequency module, which is available in different parts of the world for, I guess, different frequency bandwidth restrictions. And yeah, so you can choose different modules based on your application, whether you're trying to focus on throughput or power consumption or distance and whatever's applicable there. So we've got a little graphic of the different channels that are available for the different frequency bandwidths. The physical layer also provides us with a few interesting, nice features like link quality. So it'll keep track of the the quality of the link, which is indicated by like packet drops and that kind of thing. It also will track the receiver energy detection, which is related to the received signal strength indicator, so you can tell how strong your wireless signal is. And you can also, through the firmware, hard set the channel that you're going to be operating on. So we've got a little graphic here of the physical protocols packet structure. So it has 32 bits of preamble, which is used for synchronization operations, just to get the packet in sync, and then the packet is defined by a start delimiter, and after the delimiter, it'll start parsing the actual packet itself, which begins with for the physical layer, header that contains the length of the packet, and then the payload itself, which it'll just cycle and take in the whole payload based on what the header length was defined to be. And we'll come back to this in a little bit. So here you can see how the wait, sorry, 1 second. Did I? Oh yeah, kind of. I guess I sort of glossed over this picture here of the packet for the MAC layer. So it's got the frame control and sequence number and address information. So that's where this is 0 to 20, but for the XBee that'll be modified for 64-bit addressing or 16-bit, and then the payload, and there's a checksum on the end. So in this graphic you can kind of see how that sort of nests inside of the physical layer, which this will be more relevant when we get to forming packets later with the XBee module. So there's a couple of different node types in 802.15.4. You have full function devices and reduced function devices. Full function devices have all the capabilities of the module, and they can act as a coordinator for your network. So they're able to transmit to whoever they want. They can stay on all the time and can manage a network if you need them to. Or they can act as a router in a ZigBee network when we get there. Then you also have reduced function devices, which are, their purpose in life is mostly for saving on energy. I mean, wireless sensor networks, it's an important aspect since battery life is generally limited, but they only communicate with the full function devices, and that's all they can do. They can't manage anything. They don't do anything but basic communication with one full function device, which ends up playing a part in the topologies, which is the next slide conveniently. So there's 3 different topologies listed in the XBee documentation, but there's essentially 2. You have point-to-point / peer-to-peer topology, where each node in the network can just sort of communicate with ones directly connected to it. And then you have star / point to multipoint. So you can have full function devices communicate to each other. And then you have, like over here on the side, these, you can't really see too well on here which ones are shaded, but the reduced function devices are just communicating with this PAN coordinator here in the middle. And that sort of ends up forming this star topology, as the full function devices can relay messages between each other, and then you end up with the star topology by them having their own reduced function devices connected to each endpoint from the full function devices. So ZigBee Networks. ZigBee is a standard held by the ZigBee Alliance, and it builds on top of 802.15.4. There's a few different little variations of this, sort of like I mentioned the DigiMesh earlier with that's proprietary for Digi, the people that make XBee, and it's just an offset from ZigBee. ZigBee has the same sort of goals. It's designed with the same things in mind as 802.15.4, which is mostly a good balance between range and low power and simplicity, and it's targeted at applications like controls and home automation and medical applications, and sometimes toys use it as well. So I've got a graphic here that sort of shows the side-by-side for the OSI model, and then the ZigBee stack and the 802.15.4, how they sort of combine on top and cover the entire OSI model. And here we have a list of the device roles. So this side over here, you've got the 802.15.4 specific ones, full function, reduced function, and then the possibilities that the full function device can function as. And when you get over to the XBee, you can see it's just the same. The devices in the XBee network tend to just be the full function devices. However, you can have a reduced function device act as an end device in XBee. So the different parts of the ZigBee network, you have the coordinator. You only have one coordinator for network. It allows other nodes to join via a PAN ID, which is Personal Area Network. The coordinator is also responsible for keeping any security settings you might have, and also it organizes the ZigBee network. The routers are they have a lot of similar functionality as the coordinator, except they don't handle PAN ID and they don't handle the organization of the network. But as far as routing goes, they're fully functional, and when you're searching for, I've got a graphic later, I'll explain this a little better, but whenever you're searching through a network to find a route from one node to another, the routers are able to pass messages along back and forth between other routers and keep track of end devices in the network. And then you have the ZigBee end device, which is mostly just used for sensing, and they just talk to their associated router. They can't relay information between other end devices, between each other, and they're useful in the fact that it's easy to schedule sleep cycles with them, since they're not responsible for routing in the network like a router or a coordinator is. So here's an example of the ZigBee network topology. So you see here we've got the end devices represented as yellow circles and routers as blue, and the coordinator is the green circle here. So they end up sort of forming a star topology with the way the routers are connected, and the end devices are like the points of the star on the routers. There's a couple different routing algorithms that I've seen used with different ZigBee networks. However, the primary routing algorithm is AODV, which is Ad Hoc On-Demand Distance Vector Routing. AODV routing is a robust routing algorithm, except it has a lot of overhead because every time it needs to send a message out, it doesn't store an entire table on the individual nodes. It finds the routes as it needs them. So it has to flood the network and find the route. And once it gets the route, it'll take the fastest route to the destination and then use that to send a packet along through a network. So it's a lot of overhead to search through the network to find it. However, whenever you have like a node die in a network or something, it doesn't suffer from stale routes where you might have a stored route that has a broken node inside of it, or maybe the topology of the network has changed and the same route can't be used to get to a destination node. So it's robust in the fact that it always gets a fresh route each time. So you don't have a lot of packet drops from old routes. And even some robust algorithms will keep maybe short or expiring routing tables on each node, but AODV just keeps a list of neighbors connected to it. And when you're using the XBee modules, you can, through a type of command to the module, you can have it return neighbors that it's been keeping track of on its table. So here's a diagram that shows node number 1 trying to find a destination or a path to destination node 8. So it just kind of floods the network with all these different, with a route request, and then the destination echoes back with the shortest route available, and it goes to the source, and then it takes that route. So every time you send a message out, it has to do this. So now we'll get into the particulars of using the XBee modules. So the Series 1, again, no point-to-point, we're not going to be using it for the lab. The advantages to Series 1, though, is communication is a little faster, again, because there's no overhead, as mentioned in the previous slide. There's no coordinator that needs to organize paths or anything, it's just point-to-point. So it's easy to use, and you can transmit a lot more with it in a smaller amount of time, and you can broadcast as much as you want. The Series 2, again, you have access to multi-hop. However, you can only do so many broadcasts at once. So whenever we're working on the lab with the ZigBee modules, you want to be careful, since we're all going to be on the same network, how often you're broadcasting. So if one of you has like some screwed up code and you're constantly broadcasting, you'll end up locking everybody else out of the network. So it's not been a problem in the past, though. And it's got a limitation of 10 hops. So it can only travel through 10 different nodes to get to a destination. So I didn't get a chance to update this slide. This is an older version of the program X-CTU, which is used to configure the nodes, or the XBee modules. It's been updated drastically, and it looks a lot nicer. It's a lot easier to use, and has a bunch of tools that help show you stuff about the network and the module itself. But this older version is still available, and sometimes I do prefer it just because it's a little more compact, and since it's so small, it doesn't take a long time to load. So when you're setting up an XBee, usually you get a device like this one pictured here. This is from SparkFun. It's called a XBee Explorer board. It's pretty much just you connect the XBee to it, and that chip in the middle is an FTDI chip that translates UART to a serial port on your computer, or a virtual serial port created by the driver. And since this thing just communicates through UART, this program X-CTU just kind of opens up a big interface that allows it to go through the UART and configure the different settings of the XBee. So whenever you're plugging one in and configuring it, you get this list of COM ports available. Select the COM port it's on, set a baud rate, and then you can configure the XBee. So once it's configured, depending on the firmware that's on it, it gives you a variety of different, well, it has function sets here, but these are all different firmwares available for the XBee ZigBee modules. And then also pulls up all the parameters that it read from here. So you can see I've got, well, the one in blue here is one I've set, so that was a PAN ID I was using. And it communicates to these devices. Each one of these different settings are referred to as an AT command. I think some other wireless devices also use AT command. I'm not sure if it's in the same context or not, but when I'm referring to it, it's just with reference to these XBees. So AT commands are used to configure different settings on the XBee, and this interface just pretty much pumps these commands to the device that you're configuring. So whenever you set up XBee Series 2 or ZigBee network, you have to ensure that you've selected a coordinator, like I've got highlighted here, for the network. Oh, this one's actually the ZNet, so it's still ZigBee, but that proprietary modification of it. So you have to have one coordinator for the network, and then you want to set everything else out as a router or in-device if you need to do some sort of power-saving application. For the lab, we're just going to have everything. We're just going to have one coordinator, and everybody else will be a router. So the basics, you just need to configure. Once you've set routers and coordinator, you just need to set a PAN ID, and for the most part, all the other default settings will work just fine for you. So I mentioned there was a transparency mode that they come with default, but what allows you to do more interesting things with the XBee is through access of the API mode, where you construct your own packet, which is defined by the documentation on Digi's website. And that allows you to specify target destinations with different data packets. It allows you to configure AT commands while your code is running. Pretty much gives you full access to the XBee module. Whereas with the transparency mode, you can't specify destinations, and you're not able to, well, in a really, really slow, inefficient method, you're able to configure parameters of the XBee, but it's nothing useful for us. So for the Series 2, if I flip back here real quick, you can see some of these are labeled with API on the end, these firmwares. The AT is the transparency mode for the Series 2 modules, but we'll be selecting API, which allows you to communicate with constructing your own packets. So this is a look at the packet structure. So if we're looking at this from the perspective of like writing code on the RX63 end, what you'll have to do is you'll declare a character array, and you'll have to fill it according to the specifications of the API packet, and then the subtype of packet that you'll be constructing based on whether you're transmitting just a message between modules or sending a configuration command to the module itself. So you see it starts with a start delimiter. You have 2 bytes for the length of the packet, API specific structure, and then at the very end a checksum. So you see this is, you're pretty much just filling out the MAC protocol packet structure when you're making one of these, and then the module itself will then handle the physical, like the synchronization header and the other properties for the physical layer packet. So we'll look at the most basic type of API type, which is the ZigBee transmit request. So you'll fill out the API structure with each packet will start with an API identifier, which this one begins with a 0x10 to specify a transmit request. Then inside of that you have a frame ID, which if we looked back earlier, that's part of the 802.15.4 structure. So you can set that to a 1 if you want to get an acknowledgement, or you can set it a 0 if you don't care whether it made it to the destination successfully or not, or you just don't want to bother handling the acknowledgement. It's then followed by a 64-bit destination address, then a 16-bit network address. You can set each one of these to broadcast based on whether, like you can set 16-bit to broadcast if you don't know or if you want to specify a 64-bit, or you can set 64-bit to broadcast if you don't know 16-bit, or you can specifically set them both if you think you might have duplicate 16. Okay. And yeah, so the receive packet contains API identifier of 90 in hex. You have an address, 64-bit address, and 16-bit address of the transmitting node. You have this options byte, which gives you broadcast address packet acknowledged. So I've never used these options here, so the manual will explain what these do. And then the data. For the lab, I don't think we're going to have to deal with a lot of these like little specific options. And here's the API frame for the AT command. This is where you construct a very large section in the documentation, which goes over all the different aspects of the module that you can modify yourself. But these start with a frame ID, or well, the API identifier of 08 hex. You've got a frame ID for the acknowledgement, the AT command, which is represented by 2 bytes. So you have 2 characters that will represent different type commands, and then a value. So sometimes you are setting something, and if you want to read a parameter like the pan ID from a module, you can request, I think pn is the AT command, and you don't enter value, and rather than setting a pan ID, it will just respond to you with the value that's currently stored. Do I go over that? No. So there's an example frame for the node join parameter. So it's basically filled out as I said, and then you have an in and a j and a checksum for that. The checksum, thought I had a slide for that, guess I don't. Yeah, you'll have to look at the documentation for the checksum. There's a really simple method for calculating it. So here's a few more examples of AT commands. So you see you got the 2-character identifier, and this is a clipping from the documentation. So they vary wildly in the things that they can do. So it just gives you full access to different aspects of the activities. You'll have to probably set different aspects of the module. Specifically, since see up here, I've got the picture of the USB to FTDI breakout board. I only have a limited number of those. These might not be accessible all the time, so you might have to manually create your own packet with the ARC63 in and have it configure the module itself without the ease of having this graphical user interface and a serial port on your computer to configure it. Shouldn't be too bad, considering you probably won't have to modify too many parameters. And before we hand out the XBee modules, I'll go ahead and pre-configure them for most of the settings that we'll need. And it'll be up to you, like design decisions or algorithmic, modify the settings as you need them. So another AT commands. Commands interact with the packet and sending it to the module. It just stays that module. It doesn't get broadcast. And I know I've already said that, but it seems that that's a common confusion whenever I'm trying to, whenever I suggest using AT commands or somebody starts first time. I think there's a few exceptions since there's so many different AT commands possible where it might interact with the network, but for the most part they're just for that device. Yeah, and that pretty much covers everything for the basics for XBee.